Hello students, in this video I will draw the ray diagram of compound microscope and find an expression for angular magnification or magnifying power in details. A compound microscope consists of two lenses, namely objective and eyepiece. This lens O is the objective which is nearer to the object, and this lens E is nearer to the eye, known as eyepiece, and eyepiece the focal length is large and objective focal length is small. A object AB is placed just outside the focus of the objective. One ray will pass through the optical center and which moves undeviated. Another ray is a parallel ray that after refraction will pass through focus. These two refracted rays meet at this point, so the image will form here. A1 B1 is a real image of the object AB and which is magnified. Since AB is the object, so UO is the object distance, and since A1 B1 is the image, so this is the V0 is the image distance. Magnification for objective, let us denote by MO. This is size of image by size of object. In this case, A1 B1 is the image, AB is the object, so we'll write A1 B1 by AB, and that is equals to image distance by object distance, that is VO by UO. This A1 B1 will now act as an object for eyepiece, and it lies between focus and the optical center of the eyepiece. So the eyepiece will produce a virtual, magnified and erect image. To get the image, we first allow one ray to pass through the optical center, which will move undeviated. Now we will do the second ray, which is parallel to the principal axis, which after refraction will pass through the focus. These two rays are diverging rays moving away, so they will never meet. So we will produce them in the backward by dotted line. This dotted line meet at this point, so this is the image and this is a virtual image. Let A2B2 is the virtual image which is magnified, and the distance of the image from the eyepiece lens is suppose capital D, least distance of distinct vision. Now we will find an expression for angular magnification or magnifying power. It is defined as the ratio between the angle made by the image at eye when at least distance and the angle made by the object at eye when at least distance. In this figure, A2B2 is the image which is at least distance, and it forms the angle beta at the eye. Eye means eyepiece. Here the object is not at least distance, it is far away from eyepiece. So we have to bring the object at this point. We have to imagine this object here at least distance. This is least distance, so we have to imagine object here. To get object here, let us draw a parallel line. Now this is the object. Let us call this as A3B2, and this object is at least distance. This is imaginary. Now draw the line from the object to the eyepiece. Then this angle made by the object at the eyepiece is called alpha. So angle made by the image is beta and angle made by the object is alpha, and both are at least distance of distinct vision. So magnification m equals to beta by alpha. As we know, tan theta becomes theta when theta is very small. By that logic, we can write tan beta equals to beta and tan alpha equals to alpha. Now we will find tan beta from this figure. A2 B2 E in triangle A2 B2 E, beta is tan beta equals to A2 B2 by B2 E. This is the triangle A2 B2 E, A2 B2 E. Therefore tan beta is perpendicular by base, that is A2 B2 by B2 E. Similarly, we can find tan alpha from the triangle A3 B2 E, A3 B2 E. In triangle A3 B2 E, tan alpha is perpendicular by base, so A3 B2 by B2 E, tan alpha A3 B2 perpendicular B2 E base. So what is tan alpha? A3B2, A3B2 by B2E base. Now we will substitute tan beta and tan alpha in this expression. Now tan beta is A2B2 by B2E. Now tan alpha divide, we write into, so we have to take the reciprocal. So B2E by A3B2. Now B2E and B2E will cancel out. From figure, it is clear that A3B2 is equal to AB. So we can write A3BT 2 equals to AB. So the expression becomes A2B2, A2B2, and what is A3B2? This is AB. Now here we will introduce A1B1 at the denominator as well as at the numerator. Now what is A1B1 by AB? A1B1 by AB is MO, magnification of objective. So in place of A1B1 by AB, we have substituted MO, this MO. This eyepiece is behaving like a simple microscope where the object is between focus and center of curvature, and its magnification is ME equals to size of image by size of object. In this case, image is A2B2 and object is A1B1. Since this eyepiece is behaving like a simple microscope, so we'll use the expression for magnification of simple microscope. That is ME equals to 1 plus D by FE. So what is A2B2 by A1B1? A2B2 by A1B1 is ME. This is the formula for magnification of a compound microscope, that is M equals to MO into ME. Now we will substitute the value of M0 and ME, this value, in this expression. MO is VO by UO and ME is 1 plus D by FE. So this is the expression for magnification of a simple microscope, compound microscope. Now special case. The distance between the objective and eyepiece is known as L, length of microscope. This L is the distance between O and E. As we know, when the object AB comes closer to the objective, the image A1B1 will move away. Now A1B1, the object AB can go maximum up to F0, but it cannot go exactly at f naught, because if the object placed at f naught, the image will be virtual. Okay, so this object distance is not f naught, is nearly f naught. Using sign convention, we put minus sign and object distance is nearly f naught, that is the object is placed almost at the focus. Now this image A1 B1 will move. How much they can move? It can move up to E, almost E, but it cannot touch E or cannot go beyond E. So the maximum distance of V naught is actually L. So we put V naught equals to L and substitute these values in this equation. We will get, this is the final expression for angular magnification of a compound microscope. Thank you very much.